So we are beginning off with this portions for module 6, which is the finite word length effects. It basically deals with the processing of binary information and the effect that happens because of the reduction in the size of the data. That is why it is known as finite word length effect. So basically, as mentioned over here, we have to learn about the finite word length effect in DSP systems. We have to learn about the effects in IAR system, and we have to learn about the effect in FFT algorithms. So what basically happens is that you have a 8-bit number multiplied with another 8-bit number, which will produce a result of 16-bit variant. Now, if it is a 8-bit processor, this 16-bit may not be accepted. So in situations like that, this 16-bit will have to be reduced to 8 bits. So what would happen is we would keep the significant bits and we will reject the least significant bit. So this is an example of quantization operation. So this quantization is basically the process of elimination of the lower order bits as mentioned over here, and it can happen in two ways, either truncation or rounding. So what happens in truncation is that we have this 8 bits out over here. We have the binary version over here and the decimal fractional part is there. So this is 0011. 0011 is here. When we truncate it, that means we reject all the higher bits or the lower significant bits. We have this in the form of 0.0011. So if you look over here, the all bits less significant than the least significant bit are discarded. So least significant bit is the one over here, and all the ones after that are rejected. So that is basically truncation. So if you consider this value out here, this value's by decimal version would be equivalent to 0.1992185 and precisely. And if we consider these 4 bits, it will become 0.1875. So this is creating an error in the approximation case. So if you look over here, the difference is almost like 0.012 something. So which means there is a difference in the existing value. So the value will be changing due to quantization or either by truncation or rounding. So what we looked here is the matter of truncation, and then we'll look into the matter for your rounding off. So what happens in rounding off is the fact that if we have a bit like this, like 11010, it can be either taken as 0.110. If you want to reduce it to 3 bits, it can be taken to 0.110 or 0.111. So we are rounding it off to 3 bits and the closest one will be chosen. So when we do this rounding off process, what we do is we choose the one that is closest to the original value. So if you look over here, this original value 0.11010 is decimal version is 0.8125, and when we consider it as 0.110 and 0.111, its equivalent is 0.75 and 0.875. So now when we take the difference with respect to the original value, and we can see that the difference is the same value, 0.0625 here and 0.0625 here. So in this particular case, either one can be chosen, either this one or this one can be chosen. But if it is another situation where there is a difference between the original value and the rounded off value, we'll choose the one that is closest to the original value. So now we'll learn about quantization steps. So quantization step is nothing but the difference between the two approximated values or approximated values. The difference will be given by this quantization step. So it can be either this value or this value. If a value exists over here, its nearest approximation can be given by this one or this one, but the distance between this value and this one will be constant at every point or step. So this is known as a quantization step size. So and this diagram basically shows you quantization steps. So I hope it is clear. you have quantization steps defined like this, where you will have the values that will be approximated to the value that is given by this horizontal level of the step. Now if a value exists here, if it is equal or at the midpoint of this axis, it can be approximated to either this value or this one. But if it is at this point, it will be approximated to this value. So that is a concept of a quantization step size, and the distance between this quantization levels will be known as the quantization step size, and it is dependent upon the bits size. So we'll give an explanation over here right now. Now we have designed filters, IIR, FIR and all those kind of things, and all the coefficients that were derived as part of that design procedures lied between the values -1 to +1. You might have noticed it while designing. Everything was obtained in the value range between -1 to +1. And when the b-bit binary is selected, you have the option of generating 2^b binary codes from that particular bit binary, or meaning the fact that if you have 4-bit binary, then you can raise 2^4 set of binary codes. And if you have the range that is defined by -1 to +1, then r will be equal to +1 minus or -1 equal to 2. Now b is the size of the binary including the sign bit, and b is equal to b minus 1. This small b is b minus 1, and that will be excluding the sign bit. So please note it. If you have a 4 decimal value, so not 4 decimal value, 4-bit value, so you might have heard of the fact that for a value ranging from +7 to -7, you require only 3 bits for representing the highest possible level, but you need another 1 bit for representing the sign or the magnitude of the signal. So a 1 over here will represent plus, and a 0 here will represent minus. So in that case, you have the range that is lying between +1 and -1. That is already clear, and that will be equal to 2. Now this b is a total number of bits. So this, if you look over here, this 4 is like the total size of the binary including the sign bit, and the small b is actually b minus 1. So here it will be equal to 3, which represents a value that is 7, and that will be equal to small b, and it will be equal to b minus 1, which will be the size of the binary excluding the sign bit. So using that particular points, we can deduce a formula for the quantization step size. Quantization step size will be given by r divided by 2^B. Remember, this b is the size of the binary including the sign bit. So r will be q will be equal to, that is the quantization step size will be equal to r by 2^B, which will be 2 by 2^B, which will be equal to 1 by 2^B minus 1, which will be equal to 1 by 2^B equal to 2^-B. So please note the fact that this b is the total number of bits excluding the sign bit. So you have a formula for the quantization step size. Q will be equal to 2^-B, and please note the fact that small b is equal to capital B minus 1. Now if you look over here in this graph, you can see that you have a value a will be approximated over here, which can be approximated to either this level b1 or either this level b2. So you don't have to get it much confused, or you can approximate that a is at this point, and you can assume that it can be approximated to this level, or it can be approximated to this level. So whatever is the error involved, it will be accounted by this factor q, which is the step size. So as mentioned over here, if you are assuming a value for a, it could go to two extremes, which are represented by the levels b1 and b2, which can account for the error involved, which is e. Now the error e is expected to lie between the step size. So we divide that step size into this range of minus delta by 2 and plus delta by 2. In this case, delta is equivalent to q, and you can see that this will be plus q by 2 and this will be minus q by 2. So if you consider the difference between them, it is q by 2 minus of minus q by 2 implying the space is q. So the probability of error could be lying in this range of minus delta by 2 or q by 2 to plus delta by 2 or plus q by 2. So from this graph, what we intend to do is we intend to calculate the quantization noise power, which is equivalent to the variance. So if you look over here, the formula for variance is as follows: expected value of x square minus expected value of x the whole square. I hope you get this point. These are two different things. So expected value of a value E will be given by this particular formula, that is 1 by, in this particular case, this is a general formula, and expected value of x square minus expected value of x the whole square. In this particular case, it will be expected value of E square minus expected value of E the whole square. So expected value of E will be given by 1 by q by 2, that is a range q by 2 to minus of minus q by 2, integral of minus q by 2 to q by 2 e raised to d. Now this term becomes 0. So expected value of E as per this particular formula will be 1 by q by 2 minus of minus q by 2 integral of minus q by 2 to q by 2 e of d. Now why does it become equal to 0? So when we work on this, this becomes 1 by q, obviously this term becomes q, and it becomes e square, where the limit becomes minus q by 2 to q by 2. So it becomes q square by 4 minus q square by 4 equating to 0, and this will be 0 by q, which will be equal to 0. So when we look over here, the formula for variance is sigma square, which will be equal to expected value of x square minus expected value of x the whole square. Now what we have done here is we have found out this factor, that is expected value of E, and we have found out that expected value of E is equal to 0. So what remains here is the variance q sigma square will be equal to expected value of E square. Now we come to the previous screen, and when we consider that expected value of E square is concerned, so it becomes minus delta by 2, which is q by 2, and here it becomes q by 2, 1 by delta E square d. So the delta is taken out common because it is a constant. So when we substitute, so as we proceed, we can get this as 1 by delta by 2 whole cube by 3 minus of minus delta by 2 whole cube by 3. So this becomes this will become minus at the exterior, and this minus will become plus. So it becomes delta cube by 24 plus delta cube by 24, making it 2 delta cube by delta into 24, which makes it delta square by 12. So which makes it q square by 12, and eventually it becomes 2 raised to minus 2 into b minus 1 whole divided by 12. So this is the equation for the quantization noise power that is associated with the system when you have a qubit variant, that is being when the quantization step size is given by q, and which depends upon the size of the bits. The rest of the topic will be taken or presented in the next video.